So, today let us begin a new topic. So, this is continuing in the same vein as the other topics that I just covered. So, these would fall under the category of advanced topics. So, I will not be testing you on these topics in the examination. So, but still these are sufficiently important that you should know them. So, it is debatable whether you want to classify this strictly as being part of statistical mechanics or not, but certainly see, physics is a unified discipline that you can't really have sharp boundaries in physics. So, the topics that I am going to discuss today, namely the creation and annihilation operators in many particle systems or many body physics, is quite important for modern condensed matter physics and particle physics and so on. So, it is important for you to learn what second quantization means, especially in the context of solid state physics. Okay, so, trying to tell you roughly what I am talking about. So, you see, just as we could if you take a simple harmonic oscillator which is described in terms of position and momentum variables. So, you could do quantum mechanics in the Schrodinger picture by writing the momentum operator as minus I h bar d by dx and writing down Schrodinger's wave equation and finding the stationary states. So, alternatively what you could do is you could create and annihilate quanta of the model. So, basically you describe the creation and annihilation operators in terms of the position and momentum. But what happens is that in many cases, so in that context, in the context of harmonic oscillator, you can create and destroy basically excitation. So, that means you have a ground state and you can create an excited state from the ground state by adding a quantum of excitation. But then what happens is that in many particle physics, it is frequently the case that the number of particles in a given system can also change. So, that means not just I am not talking about the quanta which correspond to the excitations, but the particles themselves can be created and destroyed. So, if that is the case, then we really need a formalism that can describe what happens to a system which has a certain number of particles, whether they are fermions or bosons, and how to describe them if I add one more particle or remove a particle from the system. So, that requires a slightly different perspective from what I have been discussing till now, but it still uses the idea of creation and annihilation operators. So, let me go ahead and tell you how I do it. So, imagine let us start off by describing a system which is of this nature, that is you have say n quantum particles. I will tell you well, right now we will not commit ourselves to either fermions or bosons, but later we will have to commit ourselves. Right now we just know that they are one of the two and they are quantum particles. So, now imagine that I have a situation where I have these n quantum particles and naturally they have kinetic energy, but they also have a mutual potential energy. That means that they interact mutually pairwise. So, there is a pairwise potential energy which is described by this V here. Okay. So, how would Schrodinger have dealt with this problem? See, what Schrodinger would have done is that he would have said that, well, the best way to deal with this problem is to list all the stationary states, namely that I would be looking for a wave function of this type. So, I am going to say that there is an complex valued function, there is a complex valued function of this type. So, this represents, so what is the physical meaning of this? So, this means that this quantity, right, is the probability this is the probability of finding the particle, finding the ith particle, I should say, finding the ith particle in this region. So, basically this is your Ri, and this volume is basically d cubed Ri. So, so the probability of finding the ith particle in a volume d cubed Ri around the point Ri. So, and where I goes from 1 to n. So, that means the probability of is the joint probability of finding the first particle at R1 within a volume of d cubed R1, second particle at position R2 within a volume of d cubed R2, etc., etc. So, so that is what this means. So, the question is, how would you compute these stationary states? You would naturally go ahead and solve this type of equation, and you would be able to write down a whole bunch of. So, you will have many solutions to this corresponding to each eigen. So, there will be several eigenvalues. So, there is an eigenvalue problem. So, you will have many eigenvalues, and so the point is, you see, now you have to ask yourself, if the underlying particles are bosons or fermions, so where does that information go into this formalism? Basically, it goes into the formalism by virtue of imposing or realizing that there is a further constraint on the nature of this wave function. So, the constraints I am going to list here. So, if it is boson, the constraint is that if I take, so let us take for example R1 and R2. So, if I interchange R1 and R2 and keep all the other things fixed, okay, so R3 is unchanged. So, I interchange R1 and R2, right, and keep all others fixed. So, I should get back the same wave function. So, if it is symmetric under exchange of any two particles, it does not have to be 1 and 2, it can be 4 and 8 or 1 and 7 or 1 and 12. So, it can be any pair. So, if I interchange any pair, I should get back the same wave function. So, if the wave function is you impose such a constraint on the wave function and also go ahead and solve this equation. So, that would describe to you a stationary state of a many boson system. So, n boson system specifically in this context. But suppose you want to describe the stationary states of an n fermion system, what would you do? What you would do is you would impose a different constraint. You would imply you would say that the constraint imposed is basically the one which flips the sign as we exchange or interchange pairwise. So, if I interchange R1 with R2, the wave function changes sign. So, if it does, then you call that a n fermion system. So, just both n boson systems and n fermion systems have to obey the stationary state eigenvalue equation, this time independent Schrodinger equation specific, that is what it is called here. So, I am going to write this compactly in the following way. So, I am going to generalize this. So, if I interchange I and j, for example, say R I or j, so interchange R j, so I am going to write this as S times R1 R j R I R n. So S is either +1 for bosons or -1 for fermions. Okay. So this is S1 for bosons, -1 for fermions. So now I am going to continue to develop some formalism which will enable me to avoid this rather clumsy approach. See, notice what is clumsy about this approach is that, I mean, there is nothing conceptually or mathematically inadequate or insufficient about this approach, but what is clumsy about this approach is that, you see, it requires you to solve a Schrodinger equation with n particles where n could be macroscopically large. So, imagine the number of electrons in a typical solid, it will be 10 raised to something like 20 or 30 more or less. So, for a typical size sample. So, but then that's solving a Schrodinger equation with that many variables is quite silly, and you want to bypass that type of requirement and see if you can simplify your formalism, which will enable you to sidestep having to actually solve the time independent Schrodinger equation. So, in order for me to accomplish this, I need to develop some formalism. So, which is what I am doing right now. So, I am just pointing out to you that these, so by following a certain sequence of steps, I will be able to eventually sidestep having to solve time independent Schrodinger equation. Look, if you find some solution to the time independent Schrodinger equation, namely this, that there is no guarantee that that solution will either describe an n fermion system or an n boson system. So, a typical solution will not respect any particular symmetry. So, it could be quite unsymmetrical. So, it describes neither bosons or fermions. So, the first task that we have in front of us is to develop or introduce an operator that would help us in restoring proper symmetries to these wave functions. So, if you have a wave function that does not obey any particular symmetry, I want to introduce an operator that forces a certain kind of symmetry on the wave function. So, let me introduce that operator right now. So, that is called the symmetrization operator in the case of boson, or the anti-symmetrization operator in the case of fermions. So, the operator is basically described by the script B with the subscript S corresponding to +1 for bosons and -1 for fermions, and I am going to define it like this. So, this is the definition of this is the ith particle and this is the jth particle. So, now I am going to define it in this fashion. So, I permute over all the particles and okay, so that is what that is. So, this is what does, so it looks very formidable. So, let me tell you what is going on here. So, basically the idea is that if you have a wave function that is not guaranteed to be symmetric or anti-symmetric, what you do is that you force it to become one or the other. So, if S is +1, what this is going to do is that it is going to permute the sequence. So, you see, if you have a sequence of n objects, you can have n factorial permutations. So, every permutation has a certain index. So, that means okay. So, let me describe to you what I mean by that. Suppose you have 3 particles 1, 2 and 3. Okay. So, you can have a permutation where the permutation can be that I take 1, 2 and 3 and jumble it up and make it 2, 1 and 3. So, this is my permutation. So, I can ask myself what would be the image of 1 under this permutation. So, the image of 1 under this permutation is basically 2. The image of 2 under this permutation, that means 1 becomes 2, 2 becomes 1 and 3 remains 3. So, this is what it is. So, this is my permutation. Okay. So, now I define something called mod p, which is a number which tells me the number of pairwise interchanges I need in order to bring this jumbled up sequence back to the original sequence, namely 1, 2, 3. So, so in this case I need precisely one such interchange. So, if I take 2 and 3, I interchange 1 with 2 and 2 with 1, basically I interchange 2 and 1. So, that is sufficient for me to send this back to its canonical form, namely 1, 2, 3. So, in other words, this mod p in this context is 1. So, similarly, you can, if you have many more particles, so you can have a mod p which is something else. So, the point is that notice that here it is s raised to mod p. So, the only thing that matters is whether mod p is odd or even. So, if s is 1, it does not matter at all, it is independent of mod p completely. But if s is minus 1, in other words, if you are describing fermions, it really does matter. So, if it is if the number of interchanges you require to bring the jumbled up sequence back to the original one is odd, then you pick up a minus sign. If it is even, you pick up a plus sign. So, that is in the context of fermions, but if for bosons it is always plus 1. So, now I have to convince you that this wave function, so even though this, notice that this psi, even though this did not have any particular symmetry, after acting by this symmetrization operator, it is going to obey the symmetry described by this index s. So, if s is plus 1, it is going to describe a system of n bosons, and if s is minus 1, so this whole object after acting on the script b is going to describe a system of n fermions if s is minus 1. Okay, so question is, how do you convince yourself of that? And so, let me give you a simple example. So, this looks very formidable, so I do not want to scare you with general forms. So, let us take a very simple example. Say for example, 2 is too simple. So, let us try with 3. So, just like I told you earlier. So, you have 3 particles. So, you have so imagine you have a system of 3 particles and you want to convert that to a system of 3 bosons. So, what you would do is that, so if initially this does not respect any symmetry, you can convert this to a system of 3 bosons by doing this. So, so what you do is capital N is 3 and S is plus 1 because you want a system of 3 bosons. So, then 1 raised to mod p is always 1, then you have to sum over all the permutations. So, how many permutations of 1, 2, 3 are there? So, there are 3 factorial, which is 6 permutations. So, what this is saying is basically you take this and so you start listing all the permutations. There are 6 of them. So, I am going to list all of them like this. So, I interchange 1 and 2, then I interchange 1 and 3, well, yeah, I interchange 1 and 3, 1 and 3, then I interchange 2 and 3. So, I am just going to list them, right? 1, 2, 3, 2, 1, 3, right? 1, 3, 2, 2, 3, 1, then 3, 3, 1, 2, then 3, 2, 1. I think we have listed 1, 2, 3, 4, 5, 6. These are all. So 1, 2, 3, 2, 1, 3, 3, 2, 1, then 3, 1, 2. Okay, and what did I leave out? Psi 1, 3, 2, 3, 2 plus psi 2, 3, 1. Okay. So I think 1, 2, 3, 4, 5, 6. Okay. So this makes sense. So I have this is my whole story. So so this is what I get. But now this would describe a 3 boson system. Okay, but suppose I want to describe a 3 fermion system. What would I do? So notice that this doesn't have any particular symmetry, but put together it has symmetry. So let me convince you that it has this requisite symmetry. So imagine that I take this whole thing and I interchange 1 with 2. Suppose I interchange 1 with 2. What's going to happen is that this goes to this and this goes to this. Okay, so these two go to each other. So together they remain unchanged. So similarly, if I interchange 1 with 2, these two go to each other and they remain unchanged. And similarly here, if I interchange 1 and 2, this goes to this and this goes to this. So together they remain unchanged. So overall the whole thing remains unchanged if I exchange 1 and 2. Same with any other pair. So that's the reason why this works. So now let's imagine I want to describe a system of 3 fermions. So the question is, how would I do this? So I have to just make sure that I don't add up all these contributions, rather I add them up with alternating signs depending upon whether the number of permutations required to restore the sequence, the jumbled up sequence to the canonical form is even or odd. So if it's even, it's plus 1, if it's odd, it's minus 1. So the question is, how do I decide that? It's very easy. All I do is I write it down like this. So I have interchanged 2 and 1. So so that's one permutation which requires, so I have to have a relative minus sign there. Okay. Okay. So let's look at this. So if I interchange 1 with 3, I get the canonical form. So that is a minus sign. And 2 remains in the middle, and 1 and 3 get interchanged to get the canonical form. And similarly here I need to interchange 1 with 3, okay, and then 3 with 2 in order to retain the canonical form. So that's 2 interchanges, so that's even, so the sign remains plus. Okay, so so what about this penultimate term? The penultimate term is again a minus sign, because I need to interchange 2 and 3 in order to obtain a canonical form. So it's going to be R1, R3, R2, and then here the very last term I need to interchange twice, because I need to interchange 1 with 3 and then 1 with 2 in that order. So so that means this remains a plus. So there are 3 pluses and 3 minuses basically. Okay. So there are 3 pluses and 3 minuses. So this would describe a 3 fermion system. So if you're if you went ahead and solved your time independent Schrodinger equation with 3 particles and you obtained some solution which describes a legitimate stationary state, it would still not be acceptable as a physical wave function until you have properly either symmetrized it in order to describe a 3 boson system, or properly anti-symmetrized it to describe a system of 3 fermions. Okay, so that's the whole idea. So now let me describe to you this particular simple example was simply to convince you of the utility of this operator. So this operator that I was talking about, namely the symmetrization operator or the anti-symmetrization operator, as the case may be. So the utility of this has been right now clarified through this example. So now let me go ahead and introduce what I would call annihilation operator. It annihilates a variable from the wave function. It doesn't necessarily, it doesn't physically describes an annihilation of a fermion or a boson yet. So right now, so imagine an operator, there is an operator A which I define to be this. So imagine now you have a wave function which is as before, neither boson nor fermion, that it has not been properly symmetrized. It could describe a properly symmetrized wave function also, but it need not. So let's imagine a general wave function which just is some kind of a solution of a Schrodinger equation, or it doesn't have to be that either. So it just describes a complex amplitude, which describes the wave function of particle 1, particle 2, etc. So I define this operator A, which has an argument called R vector, to be basically the following. So the idea is that, so let me write it more explicitly. So I'm going to, so you have n variables starting from R1, R2 all the way up to Rn minus 1 comma Rn. So that's the last variable. So what this operator does is basically it freezes the last variable and makes it just so notice that R1 and R2 are the locations of the particles, and the particles are dynamical and they can be anywhere they want to be. So, but what this operator A of R does is it just freezes one of the variables. It prevents that. So it's as if that particle has been kind of turned into stone. You just take the nth particle and turn it into stone and freeze it at the location R. So that's what this operator does. So it takes the nth particle and freezes it and gets rid of Rn altogether and becomes R. So now the number of dynamical variables has been reduced by 1. Namely, earlier there were n dynamical position variables, namely R1, R2, R3 all the way up to Rn. Now there are only n minus 1 dynamical variables, namely R1, R2, Rn minus 1, and Rn is no longer there, it has been replaced by R. And of course, there is also, I forgot, there is a factor of square root of n for reasons that I will explain later, square root of n. So, you could also write this in this instructive way. You can write this as a integral over the original wave function which had n variables, and then you freeze the nth variable by integrating with the help of a Dirac delta function. So in other words, the Dirac delta function does the job of freezing that variable to Rn to R. Okay, so this would correspond to annihilating a particle. So not necessarily either a boson or fermion, because we haven't been careful about symmetrization. And notice that even if your earlier variables, say if your earlier wave function which contained n particles were properly symmetrized to begin with. So suppose it was symmetrized or anti-symmetrized to begin with. The moment you annihilate the nth particle, you are immediately spoiling the symmetry of the system of that wave function. So the wave function that survives, which describes n minus 1 particles, is now not going to have any particular symmetry. So the symmetry gets spoiled. So it gets spoiled, and what you have to do is you have to use your symmetrization script B operator, which I described here, in order to restore the appropriate symmetry. So that's the reason why I introduced this operator, because it's going to be useful in restoring symmetries which have been destroyed by this annihilation operator, which is partial towards the nth variable. So this is an operator that destroys the nth variable and not anything else. So it's obvious, therefore, that the end result will not have any particular symmetry. So now that we know how to define the annihilation operator, now we can describe its counterpart, namely the creation operator. So how would you go about creating a particle? So this is how you destroy a particle. So if you have n particles in your system, you destroy a particle this way. So how would you create a particle? You would create a particle by, rather than multiplying by delta function and integrate, which will freeze one of the variables, you introduce a new particle through a delta function. So this is how you do it. So this is naturally how you do it, and you take the nth particle and so this is the three-dimensional Dirac delta function if you are in 3 dimensions and so on. So you add new variable called Rn plus 1, and then you freeze it to be R. So in other words, okay, sorry. A dagger R acting on So if you have a wave function with n particles and you act the wave function of n particles by the creation operator, you end up with a wave function with one more particle, namely Rn plus 1, and the wave function also, the end result of course also depends on R. So what this describes is that you are placing another particle at the location R. So that's what you are doing. You are taking another particle that wasn't there before. So the original set had only n particles. So you are taking the one more particle, n plus 1 particle, and you are placing it at location R. So the end result is a wave function which is the original wave function times the product with the Dirac delta function that indicates that you have placed it at that location. So this is fine, except that it doesn't really respect these symmetries like I was telling you. So even if you have started off with a wave function which has n particles that's properly symmetrized to describe either bosons or fermions, the moment you either create or destroy a particle in this way, you are spoiling the symmetry of the wave function. So in order to restore the symmetry of the wave function, so what I am going to do is I am going to introduce a new operator called C of R, which has this property that it is A of R times B of S. So what it does is that, so let me tell you what this does. So, it's basically it's the same annihilation operator, but what it does is it makes sure that whatever comes to the input wave function, if it's not properly symmetrized, is properly symmetrized first. So, it's like pre-processing, it's processed food type of thing. So, you first process it by you take an input wave function, you symmetrize it to describe either bosons or fermions first, then you do this annihilation thing, which spoils the symmetry, but it physically annihilates the nth particle. But then you don't want to give partiality to nth particle. So, there is nothing special about nth particle, it could have been any one. So, in order to restore impartiality, what you do is you further anti-symmetrize the remaining particles. So, of course, this would correspond to the n, this would correspond n minus 1, because this like you are symmetrizing or anti-symmetrizing a wave function containing n particle, and then you are annihilating with a, which would reduce the number of particles by 1, and then you would then go ahead and again symmetrize or anti-symmetrize. So, therefore, you will be symmetrizing with respect to one less number of particles. So, this would then correctly describe an operator that either describes the destruction of a fermion in the system if S is minus 1, or it describes the destruction of a boson in the system if S is plus 1. See, A itself does not describe the destruction of, it just describes the destruction of some quantum particle which has ambiguous statistics. But C of R correctly describes the destruction of either bosons or fermions depending upon the value of S. Okay, and now I am going to stop here, and in the next class I will continue this discussion, and I will try to explain to you, I will give you an example which explains why this C of R does what I claimed just now. Through a simple, just like in the earlier case with 3 particles, I am going to use 3 particle wave function to convince you that it indeed does what I just described. And having done that, I am going to establish that C of R obeys a certain closed commutation rule with the corresponding. So, let me write down the other thing which I forgot to write, which is so similarly, just like you can write down the creation, just like you can write down the annihilation of a fermion or a boson, you can describe the creation of a fermion or a boson in this fashion. So, you will be creating a particle. So, you will be first symmetrizing it properly, then you will be creating an ambiguous, a quantum particle with ambiguous statistics at location R. Then in order to eliminate the ambiguity, you would be further symmetrizing or anti-symmetrizing the wave function, which now remember has one more particle as opposed to one less particle as it did here. So, here it had one less particle upon annihilation, and upon creation it has one more particle. So, other than that, it is pretty much the same. So, in the next class I am going to establish that C and C dagger and C and other types of C's obey certain commutation or anti-commutation rules depending upon whether they are bosons or fermions. So, I am going to stop here, and hope you will join me for the next class, and I am quite confident that you will be benefiting from this description quite a lot if you are going to be interested in specializing in, for example, in condensed matter physics and so on later on in your career. Okay, thank you.